Two forces F1 and F2 are given by the vectors F1 is equal to 3i minus 4j and F2 is equal to pi plus qj. The resultant force, so if we added those two vectors together, we'd get vector r. And this acts in a direction which is parallel to the vector 2i minus j. Find the angle between vector r and vector I. So what this is saying is that we've got a vector r and this bit is crucial. It's parallel to this vector, which means that I could use this vector here to work out what the angle is. Draw my I and j. Using that vector there, I'm going to consider this as a position vector. In other words, draw it from the origin. So go across by 2, let's call that 2. Go down by 1 for the negative j, let's call that minus 1. So that'll be about there. And the angle that I'm interested in is the angle that it makes with the I-axis. So I measure this angle here. Expand the drawing a little bit so I can see what's going on. I'll call this angle a theta. This is 2, this is 1. Tan of theta. Simple trig from there. Job done. Okay, let's have a look at the next question that you asked me about. This was on 8b. A boat has a position vector of 2i plus j, so that was my boat. And a boy has a position vector of 6i minus 4j, b-u-y. Find the distance of the boat from the buoy, and this was the one you wanted some help with. Find the bearing of the boat from the buoy. Right, let's just sketch in roughly what this is looking like. My boat, go along by 2, go up by 1, 2i plus j in other words. The buoy, 6i minus 4j. And at some point they would like me to find the bearing of the boat from the buoy. In other words, here's my north line at the buoy. That's the line linking up the boat and the buoy together. Can I work out that angle there? That will be, again, remember where it says from is where you do the measurements, and obviously that's my north line drawn in there. Right, to help me out with this, I'm going to just put in the position vectors that I got for my boat and that I got for the buoy. That's my first position vector for the boat, 2i plus j. I'm going to call that vector A, just to make life a bit easier. I'm going to call this vector here vector B, and that's going to be the 6i minus 4j. Now, if I want to know about the bearing of the boat from the buoy, I would like to know something about this vector here. Let's put my directional arrows on there so I know what I'm looking at. So to get that, I would have to do negative b plus a. So it's negative b plus a. In other words, negative b would go in this direction, plus a positive a would go in this direction, which would give me the resultant vector going from the buoy to the boat, which would be this vector here. Minus b plus a. Let's write these out using column notation. I like negative b. So negative, then the 6, and the minus 4. Negative b plus the vector a is 2, 1. Minus, let's just multiply through by the minus. Now this vector is quite crucial because this vector describes that line. Knowing this vector, it allows me to look at the following. Just going to create a bit more space at the bottom here by erasing this writing. minus 4 and 5. If I again use that as a position vector, go along by negative 4, go up by 5. So go along by negative 4 and go up by 5. That vector there would be parallel to this vector here. So if you like, it's going along by negative 4 and it's going up by 5. So a nice bit of trig on there allows me to get this angle here. And that gives me the angle between here and here. All I then have to do is add on the 270 degrees, which would be this 3/4 of a turn here, which you can see from here. And that would give me my bearing. Remember, bearing's always being measured from the north line going clockwise. Giving me 321 degrees. Final answer.